So, chapter 7 we're beginning today. You will need calculators. Today would be helpful. You will need calculators. This is a very calculator-heavy chapter. Okay, we're going to be doing exponentials, and we're going to be doing logarithms. They are inverse functions of each other. Technically, an exponential is an equation where the variable is your exponent. That's what makes it an exponential equation. The variable is your exponent. 2 to the x, 3 to the x, 5 to the 2.5x. Okay, something like that, where the exponent is your variable. Those are exponential functions. Okay, many things grow and decay exponentially. Populations grow exponentially. That means they grow at an increasing rate. Think about how long it's been since, how long it took. I think we're at what, 7 billion people now? Is that it? Population plan? What? Almost 8? Okay. In your lifetime, it's gone from 6 to 7 to 8. My lifetime, it's gone from 5 to 6 to 7 to 8. It takes a lot less time each time you get that big jump because we grow exponentially. It grows faster and faster and faster. Because I remember when, hey, we hit 5 billion people. I was about your age. In your lifetime, we've made 2 more big jumps. Think about it. You're living in China or in India, 1 billion people. Even if you're a 1 in a million kind of guy, that's still 1,000 just like you. Okay. Exponential growth means that it's growing. The growth factor is the constant percentage or increase. Exponential decay means it's going down. Things do also decay exponentially. The value of your automobile, your brand new car, okay, its value goes down exponentially. It starts going down a little bit at a time. The first few years you have it, it's worth a lot more than the last few years you have it. If you do like I do and drive it until it dies, till the wheels fall off. A couple 100,000 miles, baby. I want to eke every single mile I can get out of that sucker. That's what I do. Okay? And the decay factor is the percent decay, how much it goes down. The thing you most often think about with decay is half-life, radioactive decay. Okay, that is a huge thing, and it does work, and it is accurate. Okay? Now, there are a couple of formulas. Y equals AB to the X. Growth if A is greater than 0 and B is greater than 1. Exponential decay if A is greater than 0 and B is between 0 and 1. So we don't deal with A being negative. Our growth and decay is determined by the number here. And we don't deal with the number on our B. The number we're raising the power is always greater than 0. Always greater than 0. We don't take a negative number to a power. It's not a function. It doesn't work. Okay. And then we have this one we're going to be using for some problems later on, and I rewrote it up here, so I had it up available for me when I got to it. A is the amount at the start, how much we start with. Rate, R is the rate or percent in decimal form. Your percentages need to be converted over to decimals. And T is time period, how long it takes. This is a very simple exponential formula, a very simple one. They can get quite complex. This is a very simple one. Okay, we will use this to configure how much money you get after a certain period. If it's an annual, let's say an annual increase in your investment. That's not how they work. They compound. They don't compound annually. They compound a lot more often than that. It's a whole different formula. It's a lot more complex that we won't do in here. Okay? Questions about this? It's actually going to be a pretty quick, easy day today. Determine the growth or decay factor. So a 6% increase. Is this growth or decay?
Growth.
It's growth. Increase is growth. Ooh, that's hard. How do I write 6% as a decimal? So 0.06 growth. A 4% decrease. Is that growth or decay? Decay. Ooh, you guys are sharp. And 4% is a decimal? 0.04 decay. Okay. 28% increase. This is growth or decay? Growth. And 0.28. And 11.5 decrease is a decay, and it's 0.115 decay. Ooh, that's so hard. Your turn to do it all by yourselves. I have Okay, so this one is a 0.07 growth, a 0.13 decay, a 0.265 growth, and a 0.32 decay. Are we good?
Yeah.
Okay. Now, a little harder. Same idea. What we do is we look at and this is an exponential equation. Where is our variable? It is the exponent. That's what makes it an exponential equation. The variable is the exponent. What are we raising to the x power? In this first one, what are we raising to the x power? 0.5. The 2 is not part of the exponent. 2 is not done it. Remember, the x only goes to what it's being applied to. The exponent goes to that. Then you get multiplied by the 2 out in front. So our growth or decay factor is this right here. Our factor is 0.5. Now, growth or decay depends upon if that number is more or less than 1. This is less than 1. This would be decay. Because what we're doing is we're taking half each time. So it's going down. Every time we increase the exponent, we're taking half. When x goes from 1 to 2, we take half of what was there before. 2 to 3, we take half of what was there before. That's what that 0.5 is. It's half of every time we multiply. Okay, so that's why it goes down. It's going down by 1/2 each time for that exponent. That's why it's decay. So I look right here. Our factor is 1.2. Is this growth or decay? It's growth, because I take whatever I have times 1.2, times 1.2, times 1.2. So this would be growth. On the next one, growth or decay? Growth. And what's my growth factor? 2. And on this one, growth or decay? Decay. And my factor? 0.6. Like I said, easy peasy today. Okay, same thing, growth or decay, and even though it doesn't ask for it, I want you to give me the growth factor as well. Okay. First one, growth or decay? Growth. And the growth factor is 5. Growth or decay? Growth. And our growth factor is 2.8. The 1/2 in front has nothing to do with whether it's growth or decay. Growth or decay? Decay. Decay. And how much? 3/7. And the last one? Decay. And it's 0.3. Okay. So this is where we're going to be using this formula here. A is our initial amount. R is my rate. and T is our time. So we need to identify when we have a problem what A, R, and T are. So in this one here, this is our initial amount. I earn $10 an hour and 5% cost of living every year after that. So this is my A. This is my R, but I need to write it as a decimal. 5% is 0.05. And then this is my time, 3 years. So I plug it in the formula. I'm going to tell you what I'm looking for on the test right now. I am looking for this formula filled in correctly. A of 3, because it's 3 years. So the amount I'll be making after 3 years is what I started with, times 1. Is this plus or minus? Is this growth or decay? It's growth, so it's going to be plus 0.05 to the third power. And then the numerical answer that goes with that. Now, when you're doing this on your calculator, because you do need to do this on your calculator, you don't want to do this by hand. Okay? Take the 1 plus 0.05 to the third power, take that times 10. Okay? So you have to add inside the parentheses first, and then raise that to the proper power. And you will be getting $11.58, because we're going to round up. 2 decimal places because it's money and you round up. Okay. That's on your test. That's what I want to see. I want to see the formula filled in. I want to see the numbers put into the formula. And I want to see the numeric answer. That's exactly, that would be a perfect answer to the question. I don't want just the number. I need to see you write it in the formula. I will not give full credit if the formula is not filled in. Okay? So let's do the next one. Same idea. Our amount after how much time are we talking about? 7 years is equal to how much are we starting with? 11,000. And our rate is 1. Are we going up or down? Down. It's depreciation. We lose. And this is it depreciates exponentially. So we want to do minus 0.12 to the 7th. Because it's decay, we subtract it. Always 1 plus or minus whatever the rate is. Yeah, that doesn't change. It's the A and the R and the T are the only things that change. I know it's still a lot. So your car is now worth $4,495.43. Although that's not really, you can't really get that accurate on what it's worth to the penny. It's about $4,500 after 7 years. That's actually not bad. Okay. Questions on that one? Okay, you invest $500 in a savings account, earn 3.2% interest. So let's set this one up. A of how long? 5 equals, how much do we start with? 500, and we get 1. Growth or decay? Growth. Plus 0.032 to the 5th power. And no savings account that I know of anywhere will ever give you 3.2% anymore. When I was your age, that was very common. Now it's like more like 0.025%, which means it'd be 0.00025 is what you multiply by. Savings accounts don't pay squat anymore. Banks don't do that because they're cheap. So after 5 years, you will now have $585.29. Now, that doesn't seem like a lot of money, does it? You're really not hanging on. Change it to 10. Instead of 5 years, do 10 years. Everything else, just do 10 years. So in 5 years, we made $85 off our investment. In 10 years, we made $185. That's not a lot. Do 15 years. Do 15 years. $801. We've almost doubled our money. There's actually a formula to figure out how long it takes to double your money. But the thing is that we gained $85 in the first 5 years. In the next 5 years, we gained $100 on top of what we'd already gotten. So it keeps going up. The amount of money you make each year does increase. Eventually, you start making a lot of money in a hurry. But you have to have patience and let it sit there for a while. It's one of those things. Like I said, savings accounts now really aren't worth much other than a safe place to put your money, so it doesn't disappear on you. You just don't make any money off of them anymore. They're not, like I said, they used to be halfway decent, now sucks. Okay, so we're just going to set up the next one, not worry about solving it at this point. So my amount in how much time? 7.5 equals 17,562 times 1 minus, thank you, 0.045 to the 7.5. And you can type in decimals to raise your exponents. It doesn't have to be whole numbers. Okay. So what time are we out of here? So I want you to do, go ahead and do all 3 of these. It shouldn't take you very long to do them, and then we'll get to the different interesting stuff. Okay, so let's do these. So the first one, the amount after 3 years is 12 times 1 plus 0.04 to the third, and you get 13 point, you round up $13.50. Okay. The next one, your amount after 4 years is 700 times 1 plus 0.026 to the 4th power, and you will have $775.69. And the last one, the amount after 5.5 years will be, you start out with 52,311. And this is an increase again, so it's plus 0.035 to the 5.5. 63,207. This is not 2.5 men. We don't have half a person. Whole people. We do not have part people. Everybody is an individual. Everybody counts as one. Even if they don't have all their stuff, they still count as one. Okay, now the fun part. Okay. Graphing exponential equations. And the exponential equations all have the same basic structure, just like all linear equations, all are straight lines. All quadratics are all parabolas. They're just moved and shifted, made wider, skinnier, same idea. The first one we have, the first 2 here are just basic ones. These are basic equations. You will be asked to graph on your quiz. You'll be asked to graph on your test. I do believe on the quiz I put a table of values, a table for you to fill in. I can't remember if I did it on the test or not, but you will want to make a table of values. So you have your x, and because I don't have the vertical, we're going to do a horizontal table. Okay, start out with 3, 2, 1, 0, -1, -2, -3. And we'll go ahead and fill these in together. Okay. So what am I doing? I'm taking 2 to the x power. That means when x is 3, I actually have 2 cubed. Right? So I have 2 cubed, 2 to the 3rd power. So when 2 and x is 3, y is 8. 1, 2, 3, 1, 2, 5, 6, 7, 8 is actually up here. Okay? When x is 2, I have 2 squared. 2 squared is 4. When x is 2, 2, 3, y is 4. When x is 1, I get 2 to the 1st. What is 2 to the 1st? 2. When x is 0, I get 2 to the 0. What is anything to the 0 power? 1. 2 to the -1 power. 2 to the -1 power. The negative means that it's 1 over that. So that's actually 1/2. Right? The negative means it's 1 over that. You just had a test that had that. We just talked about negative exponents. So 2 to the -1 would actually be 1/2. So I get 1/2. 2 to the -2. That would be 1 over 2 to the set 2 squared, so 1/4. 2 to the -3 would be 1 over 2 cubed, so that's actually 1/8. Now, a couple of questions I want to ask you. As x keeps getting smaller and smaller and smaller and smaller, y is also going to get smaller. And by smaller, I mean smaller negative values, right? So like 2 to the -10 is actually 1 over 2 to the 10th power. 2 to the 10th power is a very large number. 1 over that is a very, very small decimal, right? My question is, will it ever actually be 0? Remember, when you're doing an exponential, you're taking 2 times itself. Well, how many ever x's? X times. 2 times itself, x times. If I multiply 2 times 2, times 2 times 2 times 2, how many ever times I multiply 2 times itself will I ever get 0? No, I'll never get 0. I'll get really close. We're already getting close. I'll get really, 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 really close, but it'll never be 0. Why won't it be 0? Because 2 times itself will never be 0. The only way to get 0 for multiplication is have one of the numbers be 0. And 2 times itself will never be 0. So what we call this is asymptotic behavior. The idea is it'll approach the x-axis but never actually touch the x-axis. We can't graph that very well physically because it will look like it's the same thing, but technically there is a space between there. So when I go to graph this, I connect the dots, and I actually like going up instead. Okay. As we go this direction, this gets smaller and smaller. You know, it's the old problem. If I'm walking towards that wall and I go half the distance and stop, and then go half the distance and stop, and go half the distance and stop, will I ever actually touch the wall? Not if I'm covering half the distance. But practical purposes, physically, I will end up touching the wall because physically, I can't move myself a half of a millimeter. Right? So physically, I can't physically do that, but you understand the concept. I'll never actually get there if I cover half the distance every time. And that's what's going on here. It's the same basic idea. I'm multiplying by 1/2 each time. Now, if you look at the other side, what happens? Kind of in the whole graph, it starts out kind of growing slow, and then woof, takes off. And I mean, it takes off in a hurry. Exponential growth, doubling, is a huge thing. Okay, it's a huge thing. So it really is big. So think about this. and I've heard this, and this is backed up by mathematics. If you take a piece of paper, however big you want, biggest big piece of paper you can manage, because it'll take a big one. I know I'm recording. Fold it, double it over. Take that one, fold that over. So you folded it, double the thickness. Fold it again, double that thickness. Fold it again and double that thickness. So you start out with a thickness of 1, thickness of 2, thickness of 4, thickness of 8, thickness of 16, thickness of 32. If you do that 24 times, that will cover the distance from here to the moon. A thin piece of paper, doubled 24 times. That's exponential growth. 2 to the 24th. We'll take that times the thickness of the piece of paper. We'll span that distance. That's how it grows. It grows that quick. That's the power of doubling. Exponential growth. You double it. Somebody offers you an opportunity to pay $1 million, or give you a penny the first day, penny the 2 pennies the second day, and then 4 pennies the day after that. It doesn't take very long. You're going to be making a lot more than $1 million just by doubling your pennies. Less than a month. Okay, less than a month. Yes. Okay, same idea. To the 1/2 power. Okay. Want to set up an equation, set up a table. So if I have my x's and my y's, 3, 2, 1. Zero, -1, -2, -3. Now, this one was exponential growth because we're raising a number larger than 1 to the x power, so it's growth. Our growth factor was 2. This one would be exponential decay, and our decay factor is 1/2. These are nice, 2 and 1/2. Notice there's a little symmetry going on here. Okay, so if I take 1/2 to the 3rd power, that's 1/2 times 1/2, which is 1/4, times 1/2, which is 1/8. So at 3, I'm at 1/8. At 2 would be 1/2 times 1/2. That would be 1/4. And 1/2 to the 1st power. That's 1/2. And 1/2 to the 0 power is 1. That's always nice to get that one. That's the easy one. Now it gets a little tricky, but you can kind of see the pattern. 1/2 to the -1 power. That means I flip it, take 1/2 and flip it, and then make it to the 1st power, so it's actually 2. Okay. 1/2 to the -2 power, flip it to get rid of the negative, square it, you get 4. Same thing, -3, flip it, cube it to get 8. So if you look at this one, let's see, 2 gives me 4. Exponential decay. Same factor, only one's the inverse of the other. Decay declines, growth goes up. Same idea. And this is taking 1/2 half the distance each step. How am I going to run the wall? No, I'm going half the distance each time. Am I ever going to hit the x-axis? No, because I'm going half the distance between it each time. Okay, and that's how that works. Okay. Yes. Yes, for your guys' purposes, do 3, 2, 1, -1, 2, 3. I like more points. You need more points than a straight line, and this will get you used to it. Eventually, you'll learn to shorthand it. It's like, so if I do this one, I'm going to tell you right now, this one here, 4 to the x, 4 to the 0 power is here, 4 to the 1st, 4 squared is like way up here, and then I get 1/4, and then 1/16, and it just woo like that. Okay. That one's a little odd. As I take it, then I multiply what I get times 2. So in this one, you need to really be careful when you do this. You're taking 1/4 to the x power, taking that number times 2. Okay. Now, if you want to do these on your calculators, I'm okay with that. I'm okay with that. I'm very comfortable taking fractions to powers. Not a big deal. If you're not, feel free to do it on a calculator. Feel free to type in the fractions to a power on your calculator. You can do that too. You can type in a fraction. You have a little A, little fraction button. Parentheses, put in the fraction. And parentheses, put in the exponent. Then it'll give you the answer in fractions. Okay, we only got like 2 minutes left in class. I do expect this done in your notes. Okay, but I'm not going to worry about finishing it here.